operator. This meeting is being live streamed. The stream in this meeting you can consent to being live streamed. Access to the live stream. You can watch, share with others. Operator. Application of operator theory. Chapter. So in this one, this is looks like a physics application. So 12.2. 12.2. Vibrating strings and compressor rods. Vibrating strings and compressor rods. Compressor rods. So 12.2.1, the fundamental vibrating of string. 12.2.1, the fundamental vibrating of a string. Vibrating of a string. Fundamental vibrating string. So consider a string density. Consider a string density. Rho of x, which lies on the interval. Which lies on the interval. Lies on the interval 0,1 of x-axis of the x-axis and has tension T T. The equation of transverse. The equation of transverse. The equation of transverse. The equation of transverse vibrations. Transverse vibrations. Transverse vibrations of the string has the form of the form. String has the form. Rho of x. Dou square u by dou x square. Dou square u by dou x square minus t. Dou square u by dou x square, that equal to f of x comma t. Where u of x comma t is a displacement. U of x comma t is a displacement. What is displacement? The rate of change in place is called displacement. U of t is the displacement. And f of x comma t. F of x comma t is the force acting on the string. Is the force acting on the string. acting on the string. Since we are interested in the free vibrations of the string, we set f of x comma t equal to 0, nothing but initial velocity. And on the basis of physical consideration, on the basis of physical considerations, seek only those solutions which are periodic in T, periodic in T, and vanish at the end points of the interval. Vanish means to become 0. And vanish at the end points, of the interval, 0, 1, and have the form ux comma t that equal to I of x sin I of x sin I of t plus epsilon. It can verify that I of x must satisfy the homogeneous integral equation. It can be verified. That I of x must satisfy the homogeneous equation. Satisfies the homogeneous equation. Satisfy the homogeneous equation. I of x equal to x minus I square by t 0 to 1 rho of s g of x comma s I of s ds equal to 0. Where gx comma s g of x comma s gx comma s equal to 1 minus s comma s whole divided by n for x less than or equal to s, that equal to 1 minus x s whole divided by n for s is less than or equal to x. Multiplying the above integral equation by multiplying the above integral equation by under root rho of x. And writing I of x. I of x under root of rho of x that equal to phi of x and g of x comma s under root rho of x rho of s by kx comma s. We get the integral equation with symmetric kernel. We get the integral equation. Integral equation. Integral equation with symmetric kernel. Symmetric kernel. Okay. That equal to phi of x minus lambda into 0 to t k into x comma s phi of s ds that equal to 0. If lambda 1 comma lambda 2 etc. are characteristic values of this integral equation, are the characteristic characteristic values of the integral equation. Values of the integral equation. Integral equation. Then the fundamental frequencies of these strings are I1, comma, I2, etc. where In equal to under root of lambda n into t for n equal to where n equal to 1, comma 2, comma 3, etc. Okay. Next, what is the stability of rod under compression? Stability of rod 12.2.2. 12. So 12.2.2. 12.2.2. The stability of rod under compression. The stability of rod under construction. Stability of rod under construction, under compression. The stability of rod under compression. The equation of the bending of the elastic. The equation of the bending what's the bending of the of a rod When it is compressed by forces, when it is compressed by forces, compressed by forces, applied at its ends, has the form, E d square by dx square, g of x d square y by dx square plus p into d square y by dx square equal to 0, where g of x is the moment of inertia. Moment of inertia of the section of the rod with abscissa. Section of the rod with abscissa. Abscissa means x-axis. Abscissa AB, ABSCA, SSA. Abscissa means x. E is a Young's modulus. E is Young's modulus. And P is the value of the compression. Value of the compression. Value of the compressive force. Acting at the ends of the rod. Acting at the ends of the rod. If these ends are hinged joints, So y of 0 equal to y of L. That equal to y double dash 0 equal to y double dash L. That equal to 0. Where we assume at the ends of the rod are at x equal to 0 and at x equal to 0 and x equal to L. We write P by E is lambda. P by E is equal to lambda. And d square y by dx square. That equal to u. So then our differential equation takes up the form. Then dE means a differential equation takes the form. It's the d by dx of j square of x du by dx plus j of x into j double dash x into u plus j of x u equal to 0. The boundary conditions of u, the boundary conditions of u, are u of 0 equal to u of L equal to 0. Let I of x equal to u of x whole divided by under root g of x. Then I of x satisfies the satisfies the symmetrical integration. Satisfies symmetrical integral equation. Symmetrical integral equation. So I of x equal to I of x minus lambda into integration 0 to t k of x means kernel of the function k of x comma s I of s ds that equal to 0, where kernel of x comma s, kernel of the function, that equal to x into L minus s whole divided by ij lj of s under root of g of x for x is less than or equal to s. Next case. That means that equal to s L minus x whole divided by lj of s under root g of x for s is less than or equal to x. So hence proved. This completes the hence proved. Next, 12.4. control development for functional equations. Functional equations. This small chapter. 4.4 is functional equations. Functional equations. Functional equations. To illustrate how some functional equations can be reduced to integral equation, we take the help of the Cauchy functional equations. That is that f of x plus y can be written as f of x plus f of y. So we assume only the integrability. We assume only the integrability. Only the integrability of f of x. If we form the double integration, we form the double integration of two sides of the equation. Two sides of the equation. Two sides of the equation. X is greater than or equal to 0, comma y is greater than or equal to 0, comma x plus y is less than or equal to t. Then 0 to t. Integration 0 to t minus y f of x plus y dx dy that equal to 0 to t integration 0 to t minus y. So the f of x and d of x plus 0 to t integration t minus y. That is f of y, f of x, f of y, dx, dy. That is integration 0 to t, integration 0 to t minus y, f of u du, dy. That equal to 0 to t minus y, f of x, dx, dy, plus 0 to t, t minus y, f of y, dy. Consider this is equation number 1. Next page. You can use the formula. 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 d by dx of integration r1x to r2x. R1x to R2x. F of x comma y. Dy. That equal to integration r1x to r2x. F of x comma y dy minus r dash x f of x comma r1x plus r2 dash x f of x comma r1x. So from real analysis, to conclude that conclude that f double dash equal to f of t comma f dash t equal to 0 to t f of u du and f double dash 0 equal to f of 0 equal to 0, where f of t equal to 0 to t minus u f of u du. Since f dash t equal to 0 to t f of u du, so f dash t minus f dash y, that equal to 0 to t f of u du minus 0 to y f of u du, that equal to y to t f of u du. Hence from 1 we obtain next case integration 0 to t f dash t minus f dash y dy, that equal to 0 to t f dash t minus y dy plus f of t. That means 0 to t f dash t dy minus 0 to t f dash y dy minus equal to t to 0 minus f dash u du f of t of f dash t minus f of t, that equal to f of t plus f of t, that equal to t into f dash t minus f of t, that equal to f of t plus f of t, that become 2f of t, f of t plus f of t. So that means t f dash of t, that equal to f of t plus f of t is 2f of t. 2f of t. F dash t. This and those two, 3f of t will be. 3 o'clock t. That equal to t into 0 to t. F of u du. That equal to 3 into 0 to t. T minus u. F of u du by 2. Equation number 2. That means integration 0 to t. T into f of u du. That equal to 0 to t. So 3t minus 3u f of u du. That means 0 to t, 2t minus 3u f of u du. That equal to 0. So an equation of Volterra type. This is an equation of Volterra type. Hence get over. Okay. Okay, today we finish it. A very small chapter, this one. So, thanks. We finish it this chapter. Next class will be.